All right, so we got the recorder on, and just double check it is recording. All right, so we'll go ahead and talk about how to make components, how to make your own library components out of basic components. I don't really need to get into the browser because I kind of remember what I need to do. Okay, so I'll go ahead and start up Logic Sim, Java-jar.
I'm gonna adjust the lighting, okay?
Sorry?
I'm gonna adjust the lighting, okay?
Yeah, it's washing out a little bit too much. Yeah.
Yeah.
All right. So I'm giving myself, a particular assignment. I'm going. Yeah. Go ahead.
Just a quick question.
Mm-hmm.
Do you have to always use a -jar extension when opening visual programs, or?
Well, if you have a jar file, which is a Java archive file, in Windows, I think in most Linux you can double-click on the icon too.
If you have Java installed.
If you have Java installed,
Okay.
at least JRE. If you have
Okay.
Java runtime environment installed, that should work too.
Thank you.
Yeah, I'm just more of a command line person. Instead of double clicking, I just type it. Okay, so my homework assignment, which is what I'm doing right now, is to assume that I only have one type of gates, which is a NAND 2 gate, 2 input NAND. That's the only gate I can use, and I want to use it to implement exclusive OR eventually. That's basically what I want to do. So the first thing I want to do is to use a NAND 2 gate, 2 input NAND gate to implement a regular NOT, regular disjunction, and regular conjunction gates first. Turn those things into library parts, and then I'll go ahead and use those in return to implement an exclusive OR 2 gate. Okay. So I go to my gates here, and I'm pretending that I don't see any of the other gates, and the only gate I have is a NAND gate, and it is only a 2 input NAND gate. And that's it. Okay, so this is a 2 input NAND gate. I can make it narrow. It doesn't really matter because we have plenty of space on screen. And I want to turn this first into a NOT gate, a AND gate, regular AND, and also a regular OR gate. Okay, and you probably still remember how to do that. If I want to turn this into just a regular NOT gate, it's pretty easy. I just need to go to the pins here, specify a input pin, and we specify an output pin on the other side, change the facing just so that it looks nice, like that, and turn this into an output pin. And I don't really need to do a tri-state, so I'm going to turn off tri-state here. And then the output also has no tri-state, just like that. Yep.
When will a tri-state be useful?
A tri-state is useful when a particular device actually, by its nature, has a tri-state nature.
Okay.
Yep. A tri-state means it's neither. Sometimes a tri-state means in addition to 0 and 1, there's one extra state, and the chip is just not driving.
Unset.
It's not driving a 0 or 1. It's just floating. But in cases like this, we can just kind of assume that it's always driving one way or another. So this will turn it into just a regular NOT gate, right? And we can go through some simulation here. If the input is 0, the output is a 1. If the input is a 1, the output is a 0. Okay, that's a NOT gate. So what I'm going to do next is to turn this NOT gate into a component so I can use it in other applications. The way you do this is to select the whole thing. If you feel comfortable cutting it, go ahead and do it. If you don't feel comfortable cutting it, just do a copy and paste and then come back and erase it. So I'm fairly confident that we can just do that. And then the other thing you have to do is to go to project and add a circuit. Add circuit basically means you're adding your own component into the library of Logic Sync. So when you add a circuit, it will ask you, what is the name of the circuit. So I can say tax NOT. Okay, just to differentiate this from the regular NOT gate. And now the current focus is in text NOT gate, which is currently empty. So I go back to the main design here, double click to make it the active one, select again, go to Control C to copy, go to text not gate, double click on text not, and type Control V to paste it. Control C when you're in the main one, and then Control V when we are in the component that you want to create. Yep.
You can also just rename main and just create a new main.
Oh, okay, that helps too. But this also works. Now, when you're in a component screen, okay, when you're in a component screen, you will see this little icon here. Okay, this icon says edit viewed circuits sub-circuit appearance. So when you click this, it won't show you the actual circuit inside, but it does give you the ability to change the appearance of this particular thing. So if you want to change it, this is a good time to do it. Okay, when you're here, you can do labels. So you can basically just put a label here and say this is my input and this is my output, like so. So are there any questions? So you can label your your component and say this is my NOT gate. Okay. Are there any questions about just kind of playing around so that your component has a particular look to it? You can also go back to the subcomponent here and label these pins. So you can click on this one and specify this as the input pin. Go to this one, specify this one as the output pin, and switch back to here. The labeling of the pin does not show in the component. So in the component, if you want each pin to be labeled, you still need to use the text tool to do it. Do we have any questions about this part? No questions? Yep, go ahead.
What's that view you're in? Did you do edit circuit layout?
Yeah, it's between these two. This one, it's called Edit View Circuits Layout. Allows you to change the underlying circuit within that component. The other one looks at it from the outside, so it's just the packaging of the part. Yep. All right, so once this is done, I can go back to my main screen here and say, okay, this is all done. I can now delete this one. Now I want to make a regular AND gate, okay? But I can only use components that either I have created or a regular NAND 2 gate. So to do that, I go to gates again and use a NAND 2 gate. And I want to make sure that it only has 2 inputs, like that. But this time, since I want to negate the output of a NAND gate to become a regular AND gate, but this time I can use my own device here as a NOT gate, as a negation gate. So I'm now starting to use my own library parts in order to do the implementation. And I will just draw a line from here to here, and I need 3 pins, 2 input and 1 output. So I have 1 input pin, 2 input pins, and 1 output pin on the other side. So with the output pin, I'm going to change the heading, and with all 3 pins, I will turn it off. Should have done that first, so that when I copy and paste, they're all just with 2 states instead of 3. But that's okay, not a big deal. And then I'll make the connections. Oops. Like so. And now we can go ahead and play with this. So, oh wait, this one is an output pin, so change the direction, so it's now output pin. So now I go into simulation mode. This whole diagram as a whole is supposed to be a regular AND gate. So if I have a 1 on this side, it should still be a 0 on the outside. If this side is a 1, it should still be a 0 on the output. If both inputs are 1s, the output should be a 1. So I have just tested all 4 cases for a regular conjunction gate. So now I'm going to turn this one into a part 2. So I personally like to just say add circuit, and I'll just call this text AND2. Okay, so this is just a regular AND2 gate. Go back to main, Control C to copy, go back to text AND2, Control V to paste, and that's pretty much it. Now if I want to make it fancy, I will go to the sub-circuit appearance view, and this one looks particularly suspicious. Where are my pins?
ever put anything in there?
Did I put something there? Yeah, I did.
Yeah, I've noticed it looks like that with various
There
other
we go.
things.
I think I did not remove the select, and somehow it did not become effective until I have done that. But now it's here. So I can label it if I want to, and I'll just call this a AND gate. And on this side, we specify those are the inputs. You don't have to do that, but it's helpful, you know, if you want to remember which side is input, which side is output, where's your carry in, where's your carry out, and that sort of thing. So, you know, this part is kind of up to you. Are there any questions about making components? Any questions? Yep, go ahead.
So whenever I'm trying to drag, the pins are still there in the box, just box.
Could you speak up, please?
Whenever I'm trying to move my diagram, the pins are still there and just box move.
Did you turn it into the select mode here? You're drawing a box because you use the tool to draw a box, I think.
That's labeled differently. I can't go to the selection.
Okay, I'll help you out, you know, later on, you know, because right now I'm just, you know, telling people how to use the basic features. Okay, now I have an AND2 gate. Let's go ahead and do a OR gate. Okay, an OR2. So I will go to the main area here. You'll get rid of this because I have already copied and pasted this one. So we'll go ahead and implement a OR2 gate out of just NAND2 gates. So go to the gates here and draw one NAND gate. We'll change the input to only 2 inputs. And from here on, I can still use, you know, the gates that I have designed, you know, so far. So the NOT gate is going to be really helpful here, because I can use De Morgan's law so that I can convert a regular OR into a NAND, and then with a negation on the outside. Okay. Okay, I'm just going to work out the math first. Okay, just be sure. I don't want to do it before I'm sure.
NAND to NOR, and then negate the NOR.
Yeah, well, we want to implement a OR from NAND. So this is a negation of the negation of A or B. And then we keep the NOT on the outside, and then the inside becomes NOT A and NOT B. Okay, so this NOT combined with this AND is a NAND, and then the 2 inputs on the inside are just negated. So in order to do this, I just need a regular NAND gate and 2 negations. But I already have negations, so I will go ahead and use my own negation here. I need the negation for both of the inputs, so one goes here, and the other one goes here. And that's all I need in terms of gates. Now I can specify, you know, pins, 2 input pins, and this time I remember to use a turn off tri-state first. Put the other one here, and then duplicate this, put the last one on this side, change the facing, and this one is an output pin. And now it's just a matter of making connections, like so, and then we can test it. This whole thing as a whole is supposed to be a regular OR gate, so that means if I turn one of the inputs into a 1, at least one into a 1, the output should be a 1. Okay, that works. That works. And if both are, you know, 1s, you know, the output should also be a 1. That works as well. If both inputs are 0s, the output should be a 0. So this is now a regular OR gate, and I can now select this whole thing, do a copy, go to project, add circuit, and we'll call this a text OR gate. And in here, Control V to paste, and touch somewhere else, because otherwise, the packaging just doesn't work out. So I can go to the packaging here, give it some labels. So we have input, we output, and this is a just regular OR gate. Are there any questions about this part? Now you can, if you want to, make the packaging as fancy as you want to, but the tools that you have is really just limited to these things. So you really cannot make it super duper, fancy, but it's, you can change the look of it. Any questions about what I have done so far? Okay, so one more level of abstraction. I want exclusive OR. Okay, now if you look at exclusive OR as an equation, A exclusive OR B is basically the disjunction of two things. The first one is not A and B. The second one is A and not B. That's basically exclusive OR B. So I'm going to do this implementation here. I will require 2 NOT gates, 2 conjunctions, and 1 disjunction. Okay. So keeping that in mind, I'm going to go back to main and remove this. And now I'll go ahead and implement the design. We'll need 2 inputs, A, B. The negation applies to 1. Okay, so we'll go ahead and just put all the components in first. So we'll need 2 of these. We'll need 2 AND gates. So we have 2 AND gates. And 1 OR gate. So now I'm exclusively only using components that I have created, because a NAND 2 gate is not going to be useful. Well, at least one way to do it is without the use of a NAND 2 gate. We know the output of the 2 AND gates will go just to the input of the OR gate. So we'll go ahead and draw those connections first. Feed this one to here. Feed this one to there. And then this is just going to an output pin. Okay, so let's go ahead and put the pins here. And turn the facing to west. Turn off output. Turn on output. And this becomes my output pin. And then when you look at this diagram, the output of one of the negation gate and one of the non-negated inputs should go to one of the AND gate. And it's almost the same thing with the other one. So if I just kind of move this one aside, so it looks more symmetrical. This goes in one of the inputs. This goes into the other input. And now I can specify the input pins. So we can just go ahead and duplicate this one, turn it back into an input pin, and change the facing back to east. Put one over here. Put one over here and make this connection here. Now this one also needs to go here. This one also needs to go here. And now we have ourselves a exclusive OR gate. Now before I officially call this an exclusive OR gate, let's test it, right? 0 exclusive OR 0 is a 0. Okay, that's correct. 1 exclusive OR 0 is a 1. 0 exclusive OR 1 is a 1. 1 exclusive OR 1 is a 0. So I have just tested out all 4 combinations of the inputs. It's all working out just fine. So now I have myself an exclusive OR gate. Now if I want to, I can now go to here and select all of this stuff here, Control C, go to Project, Add Circuit, and we'll just call this tax exclusive OR, and go to this component, paste, and go to the component view. If I want to document it, I can say this is the input side, this is the output side, and this particular gate is an exclusive OR gate. So this way, I can now start to use exclusive OR as one particular gate, as one particular thing, if I have any design that calls for exclusive OR. Are there any questions about what I have just done? So I have done multiple levels of abstraction. It's kind of like, you implementing a function, and you can call a function from another function. That's basically what it is. Any questions about this stuff here? No questions? How many people use this time to finish the homework assignments? Both the adder and the subtractor. All right, very good. Are there any other questions related to how to use LogicSim, stuff that I just did a little bit earlier, or any general questions? In the homework assignment, the description says you can only use certain types of gates, right? Any other questions? What's for dinner? All right. Well, if there are no questions, this is it. This is the only demonstration I have scheduled for tonight. Yep. Oh, the buggy program. Okay, so let's do that. I'm not going to save this. It's not really worthwhile. Yep. Go ahead.
So yeah.
No.
Are you gonna? Would you be able to put this online somehow? The file.
On Moodle? The recording of the video or this particular file?
Oh, is there a video of this class as well?
Sorry?
Is there a video of this class as well? Oh, okay.
Yeah, it's all being recorded. The video is more useful than posting this file because the file itself is not going to show you how it is done, but the video is. Yep. Okay, so getting back to George. Okay, George has a question about one of the buggy programs. So if you're not interested in the debugging part, you can kind of go get your dinner. But I'm going to explain, how to deal with that particular program. Sounds like a fun thing to do. All right, so it is under data and number representation, and it's under this link, right? So I'm going to open it as a new tab so we don't lose the original one. Okay, which one?
Or the CDP.
Say again?
Or the very top.
The very top? This one?
Yeah, so I really want the first two, but we'll first go to that.
Okay, let's deal with this one first.
You're recording this too, right?
I am still recording this. Okay.
I'm hungry.
Okay, you are hungry. Okay.
I'm going to be the only person here.
No,
You
no.
have to leave. You can leave.
No, I'm supposed to be here all the way till 10 to 10.
Nice.
10 to 10. I'm going to be here till 10 to 10 anyway, so might as well use this time to explain something, right?
Yeah, 4 minutes catch up.
Okay, well, so
Okay, go ahead.
I do know that. So what this is trying to do is
This is a little bit beyond C++, a little bit beyond assembly language programming.
Yeah.
Okay, so let's take a look at these subroutines, okay?
I did find out what the problem is. I mean, I know what the problem is.
Okay, this is really kind of tricky. All right, so let's take a look at F first, okay? Because we want to analyze each individual subroutine first, and then we'll figure out how it's used and why there's a problem. This particular subroutine F is returning a pointer to an integer, okay? Because int asterisk means pointer to an integer. It takes x as an argument, okay, as a parameter, and what it returns is the address of x. Now, because this is in C++, there is such a thing called passing by reference, but this one is not. This is passed by value, which means the parameter only exists during the invocation of this subroutine. Okay?
Say it again.
Okay. The parameter x only exists during the invocation of this particular subroutine. It did not exist before, it would not exist after.
Because it was just a copy of the actual x.
Yes, but the duration of its existence coincides with just the invocation of the subroutine.
So upon returning
It's
from
gone.
from F, that address is BS to us. It doesn't really, it's no longer...
It's no longer the parameter x. It is now freed to be something else later on. It is deallocated, basically. Okay, so G is kind of the same thing, except we are taking the address of another parameter, okay, and the same thing with H, okay. So when we deal with this, okay, F is returning the address of a parameter. But that parameter is really no longer quote unquote existing, even though it is the location that used to store the value of the parameter is not overwritten yet.
Yeah.
Okay, may not be overwritten yet. Maybe not. Okay, so it all depends on, how we invoke, C out, the shift operator.
Yeah.
Okay, because that's basically its own subroutine call.
Oh, okay.
It is its own subroutine call. And just from looking at this code, this is a really bad idea because the address of X is a temporary thing. By the time we return to this place, that is already gone. We are no longer guaranteeing that that location is still 42.
Yeah.
So I don't know exactly what is the output of this program.
Oh no. Well, so when I thought of it, I just looked at it like both of the, especially G and H, since they take multiple parameters.
Right.
It's just returning this last parameter. So from my knowledge, I was like, okay, the output should be 42, 44, because from line whatever that is with the first CAP call, well the second CAP, it's going to print out Y1, which should be 44, because G should be turned 44.
Okay, so one thing you might observe is Y1 and Y2 are actually the same. Well,
No, that's exactly what happens.
Yeah.
Well, so what I'm thinking is supposed to happen from just the way you see the code, it should say 44, 46, and then 49, 52. It should, because that's what the function is writing.
Right.
But what ends up happening is, as you said,
Yep.
Y1, Y2 are the same, Z1, Z2 are the same.
Yep,
And
exactly.
so when you go through GDB, what you end up seeing is just, and Danny was explaining it, was that, well, that's the same memory location. So it's returning the exact same address.
And it is a memory location that is deallocated already, which means anything can grab that location and do something with it. So the fact that you're still seeing some remnant of what was there is just out of luck.
Okay.
Yeah.
And so the fix for this isn't to like get rid of a pointer, it's just don't do this.
Just don't do it. Exactly. Because, well, in this class, we will actually be able to explain the behavior of this program, just not right now. So it's interesting, and you can convert this program into a regular C program using printf, and it will behave exactly the same way. So the behavior of this program has nothing to do with C++ features. It just has to do with you're grabbing the address of a parameter, but the parameter only exists when the subroutine is being invoked. But before and after the invocation, it doesn't exist at all.
And that's the way for all parameters.
That is the same for all parameters, as well as auto-local variables.
Auto-local are the ones that are just created
on the fly.
On the fly. And so,
Yep.
I don't know if I'm murking stuff up, but so main itself is a function.
Main itself is a function. Yep.
Is there any possible way that this could occur with the arguments of main? But like, because that's what I'm thinking, like, the only time that you would ever exit main to where it's local parameters.
Main has arguments. Main actually can have two arguments. I take it back.
It
There
has two arguments.
at least two, but it might have more. I think it has more than two. It's just that we don't usually need to access the environmental variables. I think those are the third and the fourth.
See the count of the arguments, then the array. Okay.
Right. So the first one is argc, which is the count of arguments on the command from the command line, and then argv is a pointer to a pointer of characters, which is basically an array of character pointers pointing to the strings that you pass to it on the command line.
More variable,
I think there are two more for environmental variables. So I'm not 100% sure, but I think they're the third and the fourth.
Okay, but, all right, and then so the whole fix is just do not try to return addresses of local.
Exactly. The address of any local variable or parameter can only be useful within the subroutine itself. They should never ever be used outside of the subroutine. Yep. Unless it is a subroutine that you're calling from this one.
Okay, that you're going to return back to it, so it's
Right.
not okay. And then, like I said, the only ones that I got to was the next one was array.
Array. Okay. So let's take a look at this one.
And this one, so it took me a while to realize that it was even buggy. but you see what happens, and it ends up printing out what seems like A and B, because A, function F.
It has the same problem as the other program.
Yeah.
You are using the address. The program is using the address of a local variable that is auto. And auto local variables, in many ways, are similar to parameters, because they only exist during the invocation of a subroutine, and they have basically no meaning before or after the subroutine's invocation.
And an auto local is I. In this case, would be I.
Unless you use the word static in front of a variable, all everyone is auto.
So no, that's what I'm saying. In this case,
it is auto.
XR is an actual parameter.
X is a parameter,
and then
I is a local variable. Okay. Yeah, it is an auto local variable, which means it only exists during the invocation of a subroutine. Now, when you have this line here, it is still meaningful, but when it returns, that address becomes meaningless. But because A is a global variable, it can continue to store that particular address even after it is meaningless.
Oh, okay, so yeah, so the problem is at any point something else could happen that you'll be turning back garbage.
That is correct.
And then he had also, Danny had said that there was the problem lied in the fact that both the functions are, he said mathematically the same. Basically, they take up the same amount of instructions, the same size of memory.
They take up the same amount of space. So the local variable I of G just so happens to occupy exactly the same space as the local variable I of F. So when you call G, it overwrites exactly the same locations.
And that's just by chance.
And that, well, it's not exactly by chance. It has to do with both F and G have the same number of parameters, the same type of parameters, and the same number and types of local variables. So that makes their quote-unquote frame exactly the same shape and the same size. And because they are called from the same level, like one is here, and that's why they basically share the same space. So in return, what happens is, A and B will basically point to the same space. And that's why, when you look at...
you're trying to print A twice, you actually end up mangling.
Right, one is A and one is... Basically, A and B will point to the same space, so when you print A twice, it will change because of the call of G. Right. Yeah, all of these will become kind of clear, hopefully at the end of this class, because we will talk about, the call frame concept and, how subroutines are actually called and who is responsible to create or allocate a space for local variables and how local variables are deallocated. Now, since you took P300 from me,
No, didn't.
you did not? Okay. You did. I talked about it a little bit in my P300, but in this class, it will be very clear, how things are really done, underneath the hood, under the hood.
Well, then I'll button you more then. I appreciate it.
All right.
What's P300?
P300 is our pre-C class. It's called Algorithm Design and Problem Solving. So in that class, we only talk about, programming concepts. And it's not, the way I taught it was not language specific. But there are common concepts across almost all programming languages, like loops, okay? They might have a slightly different syntax, but the meaning is the same. Conditional statements, they're the same thing. Local variables, global variables, parameters, pointers. Well, we didn't talk about pointers, but passing by reference as opposed to passing by value. How to return a value from a subroutine. So we talked about all of those things, but without being language specific. And we use, I use a pseudocode language that is not compilable. Yeah. And in that particular class, students have to quote unquote execute a program by doing everything by hand, and they have to maintain a trace of how memory is allocated and modified as the program executes.
That's the course you have to take
before C.
In addition to the to another course, and then you can go on to 360 course, right?
It's 300 and then 360.
Yeah.
So 300 is the prerequisite of cisp 360, and then cisp 360 is the prerequisite of this class.
I went to a previous school before.
Right.
Here.
Yeah, as long as you know C and C++, at least pointers, you'll be okay.
Yeah. No, I went to a previous school. He taught us Java,
Mm-hmm.
and then I took 360 over at the other school where they taught us C++, and I'm taking this course and 400.
Yeah, as long as you're exposed to pointers, you will be okay in this class. Yeah. Pointers is a big deal because it's a concept that is completely lacking in Java or Visual Basic. They don't have the concept of a pointer. Any other questions? These two are really good sample programs, but we can't really quite explain it just yet. Yep.
When you compile this using a C compiler, will it detect large amounts of repeating code, like for int I through
No.
I sub 2?
No, it does not. C compilers are smart in some ways, but it doesn't really detect repeating code like what we can see here. It can do certain types of optimization, but it does not really quite recognize that there's a repetition of pattern in this code. So it's kind of like a limitation. What we think is really intuitive, easy, and obvious, is not so obvious to a compiler.
It has to do a lot of things.
Well, a compiler has a very local view. In other words, when it's parsing it's parsing statement by statement. And when one statement is completely parsed, it really has no critical memory of the previous statement. So it doesn't even have a baseline to compare to in the compiling process. But to us, it is clear, or there's clearly a pattern, because visually we can see, those 3 lines share a lot of common elements. So to us, it is really simple. But to the compiler, because it is looking at statements truly one by one, and it only maintains partial data structure of the statement that it's compiling. So by the time it is done with this semicolon and start with this one, it would have no knowledge or no memory of what the previous statement looked like. And doing that type of optimization actually is kind of difficult because the structure. So because you have to kind of write the code to analyze the similarity of the structure of code of one statement to the next one, and that's not easy.
So as far as we were more like looking at the actual bits with when we talked up with Von Neumann, but I know I'd read that his big contribution was getting the idea that the code and the data that the code operates is the same thing, so it should be stored in the same place. So F exists as the body of code itself, those lines that make up its instructions, and then obviously it has its variables, its data X and I. Are those all placed into the exact same?
Nope. Well, okay. This is a question that will be answered, later in the class. Okay, so I want to make that clear. The code, anything that is doing something, is stored at one place of memory. Okay, we call that the text. For whatever reason, it's called a text section. Whatever it has to do with parameters, local variables, return values, and stuff like that, those are stored in what we call the stack, which is a kind of like a separate space. And that's why you can have one single subroutine, which from the perspective of instructions, there's only one set. But in terms of the data, the variables, you can create multiple copies. And that's how we can handle recursion. Because recursion is only one subroutine, but there are multiple invocations of the same subroutine. And that's the only reason why it works. Because
they're not. Otherwise, we would be replicating those instructions.
Correct. And you don't know ahead of time how many times you're going to do the recursion, so that makes it impossible. Yep.
Can you take a look at my program that I made for the homework. I just don't understand why it's not doing what I need to do.
Programming.
He said.
That's a pretty general question.
Okay.
Okay, let me turn off the recorder and then we'll